I'm going to take a minute to overview the term project, talk about the big picture goals and how it all ties together with what we've learned in class so far. We've refined the term project every year based on student feedback, and students have said that they really got out of it what they put in. And so I want to give you an overview so that you know what's intended and hopefully can get the most out of it. There are 3 installments to the term project. The first one is calculation of load and interpretation of time series of both discharge and your pollutant of choice. The second installment is allocating that load that you calculated in installment 1 among the different pollutant sources in your watershed, and then choosing a best management practice to evaluate and talk about what it can do to address that pollution source. Installment 3 is cumulative. It wraps together installments 1 and 2 and includes also either a monitoring plan which addresses perhaps some of the shortcomings in the data that you identified in installments 1 and 2, or if you're interested in doing an education plan instead or talking about an alternative to the TMDL approach, those are options as well. Installment 1, why are we talking about load and not simply concentration? And what can we learn from the patterns in these time series plots? Recall this example where I ask, if I'm a watershed manager trying to manage the water quality downstream after these 2 streams mix, one has 1,000 milligrams per liter of some pollutant, perhaps sediment in this case, one has 10 milligrams per liter, which is more important. You can't know unless you know the discharge, because if this stream has a much lower flow, then you could still have an order of magnitude more pollutant load in the stream with less concentration. So this raises the point of concentration versus load. And if I'm a fish that is swimming in one of these streams, then I absolutely care about the concentration. If I'm trying to see macroinvertebrates to eat and the turbidity is making that difficult, then I would relocate from this high concentration sediment stream over into a lower concentration stream. But if I am a watershed manager and I am trying to manage the quality of the water, the concentration even of the water down here, then I need to think about load. Because, so let's think about if I'm a reservoir manager downstream of these 2 sites, I don't care at all about concentration in these tributaries. I just care about the total amount of sediment that is landing in my reservoir. And similarly, if I am a watershed coordinator managing the quality of the water downstream after these tributaries have mixed, I don't care about the concentration in those smaller tributaries. I want to have equal footing to compare all of these different loads from all of these different sources across these tributaries on even terms, so that I can know where to put my effort to try and address the biggest bang for my buck. So watershed managers, even if concerned about the concentration of a pollutant downstream, have to think about it in terms of load if you want to talk about watershed management. We talked about load in the sediment homework with the Yellowstone River, where we looked at this relationship between flow and sediment and calculated the total amount of sediment moving past Corwin Springs in the Yellowstone River and then ultimately dumping into Lake Sakakawea, and calculated the time till that reservoir might fill. We also did load calculations in the TDS homework with 2 approaches, using discharge regression against total dissolved solids, which in this case is an inverse relationship, and a specific conductance relationship with total dissolved solids, and because specific conductance was measured daily at the Powder River site. So this structure for the term project allows you to choose a site that you're interested in with a pollutant of choice and quantify that load to start thinking about how all of the sources that might be present in your watershed compare to one another, and to have a number to start thinking quantitatively about where you should try to put effort to address pollutant sources with best management practices. So a last piece of installment 1, trying to interpret the time series of both discharge, which is blue line here, returning to the Powder River homework example, the TDS homework, and your pollutant concentration. So what we did for the Powder River, recall, was take these diamonds, which were the TDS measurements, and plot a regression against discharge, and we saw this negative relationship, which is plotted here as this dotted line. Don't fall into the trap of trying to interpret the relationship here between the hydrograph, the blue line, and that dotted line, which is modeled based on the hydrograph. So these two are perfect mirror images of one another because the dotted line is calculated from the flow line based on the slope of this curve and the y-intercept. So you cannot interpret the relationship between those two lines. You can interpret it in the context of this regression, but not in the context of the plot. You can interpret the measured points in relation to the hydrograph, but those are so few here that it doesn't provide a lot of insight. This is parallel to what the situation for the sediment rating curve on the Yellowstone, where we had a positive relationship between sediment and discharge, and we modeled the sediment concentration based on discharge. So these lines are perfectly parallel based on the slope of that regression, and so you cannot interpret the fact that they are perfect mirrors of one another. In contrast, adding this specific conductance line onto the Powder River plot, this is again calculated from the relationship between specific conductance and total dissolved solids, and this line is independent of discharge because specific conductance was measured on every day, and that's how we estimated this TDS line. And so this darker gray line can be interpreted as it relates to the hydrograph. And so, because it's an independent measure, it was not calculated from discharge like this dotted gray line was. And so here, the concentration of total dissolved solids plummets a little bit when this storm event happens. That is meaningful, and we could interpret that. Whereas over here, in this next storm event, TDS, or the salt concentration, does not plummet. And then over here again, in this later storm event, it does. And so there's some insight there that we can read into it, and that would be lost on us if we were only being able to look at the modeled TDS from the discharge relationship. So depending on the data set that you have, there are two avenues here. One is that you ended up calculating or estimating, modeling your daily pollutant concentration based on its discharge, and you got something like this dotted line. Perhaps yours has a positive relationship, but basically you might have calculated your pollutant concentration based on discharge. If you did that, then you cannot interpret the relationship between these two lines. And in that case, you would spend more time talking about the limitations of the approach and some of the effects that might be masked by the approach that you took. Whereas if you have this high frequency data where you have daily measurements or daily pollutant estimates from a surrogate variable other than discharge, then you can interpret the relationship between your daily pollutant concentration and discharge. And so you can spend more time on evaluating the nuance in that relationship and thinking about what does it mean that I see a dip here, that there's dilution, and so theoretically a lower concentration of salt, if we're thinking of salt as our pollutant, in this storm event, whereas this storm event did not cause a dilution. So why was there a higher concentration of salt in this storm event, and so on. So those are the things that come out of term project installment number 1. And set the stage for installment 2, where we talk about how important are the different sources contributing to that load that you just calculated, and what BMPs can address the sources, or we'll choose one specific source in BMP, and then what will that BMP actually physically or chemically do to address the issue. So if I'm a watershed manager trying to address a water resource issue, I've got all these different pollutant sources in my watershed. Which one is the most important? We started thinking in these terms with the second assignment, where we looked at load allocations across these different sources and started playing with reductions to see where we could get the biggest bang for our buck. This worksheet that's overviewed in the template for the second installment helps to lay some of those things out in a clear way. And ideally, you're able to inform those sources with a TMDL or other planning document for your area. If not, then I've provided some pretty simple ways for you to estimate those in a cookie cutter kind of way. And if you're short on information, some of this might seem a little bit like arm waving, but it's a useful exercise to start thinking about the framework for how you could do these back of the envelope calculations to figure out what important sediment sources might look like and what kind of load reductions you're going to have to get from a BMP to be meaningful. Another important part of installment 2 is talking about what a BMP is actually going to do. And so if we think about, a lot of times people will suggest riparian buffer strips as a BMP, which can be a great BMP. What that buffer strip is actually going to do is going to be very different depending on what the sources are and what you're physically intending for it to do. If you've got a bunch of runoff from Forest Service roads and you've got this rill turning into a gully, running down and then hitting a stream down there, a vegetated buffer strip is not going to be able to do much to stop that, because you're not going to get surface area of contact with the vegetation if it's all running down in a rill or a gully like this. Whereas if you've got an eroding bank like this, and you come in and establish vegetation and put it in a vegetated buffer strip, you could dramatically reduce the rate of erosion of these banks. And so identifying what the sediment source is it an upland source like this or an in-channel source like this, and what is that BMP going to actually physically do to address the source? Another important part of this is thinking back to we identified a pollutant source in the stream. What is the avenue that pollutant source took to get to the stream? Is it a particulate or a dissolved type of pollutant? Is it coming over the surface or subsurface? Is it coming during precipitation events or in with groundwater? Those are critical elements that you have to outline in installment 2, how the pollutant gets to the stream, what the BMP is actually going to do, and part of this is a conceptual representation of your pollutant source. You can do this in a variety of ways, and I'll give you a little more insight on that. I simply did, I focused on, for the template examples, culvert replacement to reduce sediment, and so I just simply did a Google image search, and I've been pretty loose here with how you can cite that. And so the source is water running over the surface of the road because of a plugged culvert or undersized culverts causing erosion into the streams, running down the road here, as you can see after in this picture. And so undersized culvert before, properly sized culvert afterwards, so I can talk about what's actually physically being accomplished by the BMP of culvert replacement in the narrative of my term project. The last part of installment 2 is to actually calculate what the pollutant load reduction is going to be from implementing your practices. And so there's more detail on this, but it's trying to wrap together these concepts of what's it going to do, over what kind of spatial extent am I going to be able to implement this BMP, and so what effect can I expect it to have in the watershed. So in installment 1, I'm exploring data sets. I'm learning that there's not as much out there as I would like. And I'm finding data sets, calculating a daily load, getting a number that I can use as a starting place, thinking about what I can interpret from my time series of my hydrographs and my pollutant concentrations, Then in installment 2, I'm thinking about what can I say about where that pollutant is coming from? What are the data limitations there that are frustrating? What best management practices am I going to try to implement, and what are there data limitations there that are frustrating? How can I quantify the value that's supposed to be coming out of these practices I want to implement? And then I'm going to wrap that stuff together in installment 3, where I have an opportunity to talk about a monitoring plan that I'd like to lay out to address some of those earlier issues that I've identified. You also have a chance to talk in more holistic terms here. What's wrong with the TMDL approach? Are there other things that, other approaches that I'd like to be able to implement? And or what kind of an education plan might I want to put in place, just to allow people to choose one of these if you want to focus based on your individual interests and what's appropriate for the watershed that you chose. I've worked really hard to structure this term project in a way where you're going to get these big points that are important for thinking about watershed management, but affording you enough flexibility that you can work on something that's interesting to you. So I hope that you're able to learn from it and have fun with it.